Assalamualaikum and good day. I bid to everyone. Welcome back to our lesson. So yesterday we had our very first test. So I hope everyone did very well, inshallah. So today we're going to learn something new. It is called experimental evidence for back donation. Before we go deeper and further, I would like to make some revision on the formation of your complex. If you still remember, there were two steps needed to be taken in order to form a complex. For example, a carbonyl complex. The first one is the donation from the sigma HOMO from your carbon to your metal, and the second one will be the back donation from your metal to the pi antibonding of your carbon. So we're going to see that again today in a more comprehensive manner, where we are going to see some evidences where these two donations can be seen. So for a start, it is best for us to see the carbonyl bonding. We have sigma donation here, as I said, from the highest occupied molecular orbital of a carbonyl, or sigma orbital, to an empty metal orbital. It can be S, can be E, can be D, of correct symmetry. We have X, Y, and Z. So we understood here that for the orbitals to be able to overlap, they must be having the correct symmetry. So in this case, the first one, we are having an overlapping of orbital, or the transfer of electrons, or the movement of electrons from d orbitals of your carbon, sigma orbitals of your carbon. This is HOMO from the carbonyl to the empty orbitals of your metal. So the second one would be the pi back donation. Once all the electrons are transferred from sigma HOMO orbitals into empty orbitals of your metal, is now the responsibility of the metal to be donating back those electrons to your carbon. So in this case, the movement of electrons are coming from the filled metal orbital to the empty LUMO. In this case is your pi and the bonding. So there are two processes taking place here. One is the sigma donation from your HOMO of your carbon, which is your sigma orbital, to the empty orbital of your metal. The second one would be the pi back donation. The electrons are moving from filled metal orbital into the pi antibonding orbitals, the LUMO of your carbonyl. So now, if you still remember, we have talked about synergic effects, that pi promotes sigma and sigma promotes pi. So the same things are happening here. So pi promotes sigma, meaning back donation maintains electron density on carbon while preventing excessive negative charge build-up on metal. What does it mean? Because remember, I told you that your metal is electropositive in nature. So by hook or by crook, your metal needs to be staying electropositive at all time. So how does this occur? You will do some back donation, meaning your meaning your electrons from the metal will be donated back to the carbon. So by having done this, your metal will be staying electropositive, preventing negative charge on the metal, and at the same time we are maintaining the electron density on the carbon. The second one is sigma promotes pi. What does it mean? Donation makes the metal more electron rich. When you have the electron donation from your carbon to your metal, so now your metal is having a very rich of electrons, and therefore they are more willing to engage in back donation, because only when your metals are having excessive electrons, negatively charged, only then they are ready to be giving back the electrons. So we call it this as synergic effect. So for the introduction of this particular subtopic, I would like to put a very a heavy emphasis on how your metal carbonyls are formed. You must remember that there are sigma donation and we have pi back donation. You must remember the HOMO for your carbonyl is actually the sigma. These electrons, the electrons from the sigma HOMO will be donated to your empty metal orbitals. Now the second one is pi back donation. Now your metal are being populated with the electrons. These electrons will be given back to your carbon. To which orbital? Pi antibonding. Why? Because this is the LUMO of your carbonyl. I hope you are clear with this. If you are not, please ask me questions later in the Padlet or in the WhatsApp group. So as we have been giving the emphasis on this, I would like to reiterate again that the two types of bonding are cooperative, or better term as synergic. So this type of bonding is unique, not unique to carbonyl. It can also be applied to any other pi acceptor ligands. Okay, so the net effect on carbonyl is that the electron density is removed from the weakly bonding sigma level and increase the electron density in the strongly antibonding pi 2 level, because your electrons coming from sigma moving to metal giving back the electrons to your carbonyl through your pi antibonding. So we can predict two things here. One is the metal to carbon bond should be stronger and shorter than a normal single bond. I hope you still remember the strength and the bond order, and as well as the bond length of your bonds. We have a single bond, double bond, and triple bond. So the second one will be CO, carbonyl to oxygen bond, should be weaker and longer than a normal triple bond. We can make one simple conclusion here, that the shorter the bond, the stronger it is. The longer the bond, the weaker it is. So your first assignment today is for you to arrange your bond strength here, from metal to carbon, to single bond, to double bond, to triple bond, to carbon to oxygen bond. So we have 5 things that you need to arrange in whatever order you wish. It can be in a decreasing order, or it can be in the form of increasing order. So experimental evidence can be obtained first. This is the most accurate one through X-ray results, where you can accurately measure the bond length of your metal to carbon or carbon to oxygen, or we can have IR, stretching frequencies, which will reflect the bond strength. I hope you still remember IR. This is the most fundamental part of this particular subtopic. Now moving on, evidence from infrared spectroscopy. So the first thing that you have to know is this equation, that E equals to H, Planck constant, nu, equals to Hc, c is the speed of light, divided by lambda. Lambda is the wavelength. So from this equation, we can understand that your energy and frequency are in direct proportion, meaning they are proportional. The higher the energy, the higher the frequency, and vice versa. The lower the energy, the lower the frequency. So based on that understanding, now please have a look at this one. Please focus on the frequency of your carbonyl. You see, for the free carbonyl, no metal, it is unbonded, it is free ligand. So we can see that the frequency would be at 2143. When you have manganese, it reduced to 2090. When you have chromium, it reduced to 2000. And we have vanadium, it reduced to 1859. So today we're going to learn why we can have such frequencies. Remember, the hypothesis that we have made earlier was that the higher the energy, the higher the frequency. Now, this is a simple relationship that anything that is stronger will need higher energy to break it, right? So the same thing applies for your bond. If you have a stronger bond, definitely you'll be needing higher energy. And this will be reflected in your IR spectra in the form of frequency. So we agreed that your frequency will be higher if the energy is higher. Why the energy is higher? Because the bond is stronger. Okay, now let us discuss this further. So of the three organometals above, vanadium has the metal with the smallest nuclear charge. So nuclear charge actually taken from the atomic number. So from vanadium, chromium, and also manganese, you can see here vanadium 23, chromium 24, and manganese 25. So we can say that vanadium has the lowest nuclear charge because it does have the lowest atomic number. So when this happens, your vanadium will have weakest ability to attract electrons. Definitely, the smaller the nuclear charge, the weaker it is relatively to attract the electrons, because positively charged nucleus and negatively charged electrons are attracted to one another, but the strength of attraction will be lower if the nuclear charge is lower. So that's why it does have weakest ability to attract electrons, and consequently will have greater tendency to back donate electron to your carbonyl. Okay, so meaning your metal with smaller nuclear charge will be having greater tendency to be giving back the electrons to your carbonyl. We understood earlier that your metal will be giving back the electrons to your carbonyl, definitely, no matter what happens, because your metal is electropositive in nature. It must be giving back the electrons to your carbonyl. But the question is how strong, how likely the back donation will happen. So that is the big question here. So as I said, the weakest ability to attract electrons, the greater the tendency for the metal to be giving back the electrons to your ligand. Okay, hence populating the LUMO of your carbonyl in this case is the pi anti-bonding. Now the consequence is high electron density on the pi anti-bonding, and of course this will reduce the bond order as well as the bond strength of your carbonyl. So that's why vanadium is having the lowest frequency. Now, in order to understand this more clearly, let us look at this particular table. Now, we arrange manganese, chromium, and vanadium in order, in decreasing order, from highest nuclear charge to the lowest nuclear charge. So what happened next is, okay, you see number of electrons of the metal center. We have manganese plus, so definitely you have to minus 1 is 24 electrons. Chromium 24 electrons. Vanadium minus, it is now 24 electrons. You have to plus 1. They are having the same number of electrons in the metal center, but they are having different nuclear charge. Because nuclear charge depends on the atomic number. Now, what happened to the strength of attraction of metal? As I said, the higher nuclear charge, the greater the attraction. So, strength of attraction of your metal electrons for manganese will be the highest, meaning it is tightly held. The electrons are tightly held by the nucleus. But if your nuclear charge is lower, you will have less tightly, the electrons will be less tightly held by the nucleus. Okay, 25 versus 24, 23 versus 24. But for chromium, it's going to be intermediate. The strength of your chromium will be somewhat in between manganese and vanadium. So the stronger the attraction, the more difficult for the electrons to be donated back to the CO, definitely. Once you transfer the electrons from carbonyl to your metal, now it depends on the nuclear charge of the metals, whether to hold them very tightly or loosely. if the attraction is greater due to higher nuclear charge, so it is very unlikely or less likely for the electrons to be donated back to the carbonyl. So that's the first thing that we have to understand here. So what happened to the degree of pi back bonding from metal to CO? As I said, the stronger the attraction, the lower the pi back bonding. The lower the attraction, the higher the pi back bonding. Okay. Next, electron density of the LUMO. Definitely, this is understandable because degree of pi back bonding is lower. Definitely, there will be less electrons in your LUMO. The degree of pi back bonding is higher. Definitely, you will have more electrons in your LUMO. What happened to bond order? When there is less electrons in the carbonyl, the bond order will be higher. When there is more electrons in your LUMO, there will be lower bond order. So bond order is directly proportional with your bond strength. So bond strength of carbonyl, hence the frequency of your carbonyl will be higher, okay, but it will be lower for your vanadium. So remember, it started from the nuclear charge. The higher the nuclear charge, the greater the attraction of your metal towards the electrons. Hence, you will be less likely for the metal to be donating back the electrons to your LUMO, which is your pi antibonding. So this will give effect on the bond order. The higher the nuclear charge, the higher the bond order, the stronger the bond, and the lower the bond length. So because we have established earlier the knowledge that the shorter the bond, the higher the energy, the higher the frequency. This is what we are discussing now. So bond strength for of your carbonyl in vanadium would be lower. The bond strength of your carbonyl would be lower because there are a lot of electrons in your LUMO. So bond length of your carbonyl will be lower, and then bond length for your vanadium, carbonyl in your vanadium will be higher. Okay, so I hope you do understand this. If you don't, please ask me the questions later. A little bit more on this particular part. So in general, we can say the more negative the charge on the organometallic species, the greater the tendency for the metal to be donating back the electrons. Okay, because your metal is electropositive by nature, you cannot be having too much electrons. So the coping mechanism that is gonna do is by having all the electrons populated in the metal orbitals donated back to your carbonyl, which is in the pi antibonding LUMO of your carbonyl. So the greater the tendency of the metal to donate electrons and lower the energy of the carbonyl stretching vibration. So in this particular subtopic, we actually wanted to see how the strength of the bond of your carbonyl is being reflected in the spectrum. So it's going to be reflected in terms of frequency. So frequency will determine the strength of your carbonyl bond. So what's the factor? The main one is actually the nuclear charge of your metal. So the trend with metal to carbon, okay, let us see this one, metal to carbon. If you still remember, we can see that the higher the frequency of your carbonyl, the lower the frequency of your metal to carbon. Okay, so this one, as you go down, it is increasing. This one, as you go down, it is decreasing. Meaning, the relationship between frequency of your carbonyl and the frequency of your metal to carbon bond is in inverse proportion, inversely proportional. Okay. Now, so we can say that the stronger the pi back bonding, the stronger the metal to carbon bond, thus the higher the MC. Okay, so from this understanding just now, the higher back bonding would be happening in your vanadium, right? So let us see the frequency for your metal to carbon bond. It is 460, highest comparatively against chromium as well as manganese, because it does have the lowest nuclear charge, lowest attraction to the electrons, very likely to be donating back the electrons to your carbonyl. Okay, so the stronger the pi back bonding, the stronger carbon to metal bond, definitely, and the higher the frequency of your metal carbon. Just imagine if you have, if definitely, if you want to stretch something that is very strong, you will be needing a high energy, hence higher frequency. Okay, if something is weak or weaker, relatively, definitely you will be needing lower energy. So every time you see something that is higher in terms of frequency on your IR spectra, the first conclusion that you can make is that, oh, this must be a very strong bond, relatively with some other peaks. Okay. In the case of free CO, there is no pi bonding, definitely, because there is no metal, no nothing. So the pi anti-bonding of your LUMO is not populated with electrons. It will be staying empty at all time. So the bond order is definitely high. And the CO stretching, of course, has a higher energy. So we'll be having the highest energy because it does have the strongest bond. Look at this. This one, it does have the highest frequency because it does have the highest energy. Electrons are not populating the empty orbitals of your LUMO, of your pi antibonding. So the free CO has the highest bond dissociation energy. Okay, free CO, triple bond and short. The shorter the bond, the stronger it is. The longer the bond, the weaker it is. Therefore, having the highest frequency, followed by CO with one metal. So we call it terminal CO. One metal with CO, terminal CO. Or if you have two metals, we call it bridging CO. If you arrange all these according to the frequencies in increasing order, so free CO, decreasing order, free CO will be having highest frequency, followed by terminal carbonyl, and then followed by bridging carbonyl. Why so? Because your free carbonyl having the shortest bond will have the highest energy. It is the strongest, hence highest stretching frequency. So since wavelength, according to our Planck equation just now, E equals to H C over lambda. When the energy is higher, the wavelength will be lower. So no pi back bonding. But for bridging CO, it is having the longest bond, weakest bond. So that's why we need the lowest energy to break it. And then lowest stretching frequency, because frequency and energy is proportional. And since wavelength and energy is inversely proportional, the lower the energy, the higher the wavelength. So why this is happening here? Because we have highest degree of pi back bonding. Why highest degree of pi back bonding? Because bridging CO has two metals. Compared to this one has no metals at all. Okay, that's all for today. I hope you do understand. If you don't, please WhatsApp, or please put your question on the Padlet. Remember that I have asked a few questions just now, or maybe one question. Please answer in the Padlet. Thank you very much for your attention. See you in the next video. Assalamualaikum.